Okay, so we're going to work this last practice problem on coagulation. This has to do with calculating what they're calling aerosol half-life, the time to reduce the number concentration by a factor of 2. We're given a table that has a bunch of initial number concentrations that vary by orders of magnitude. So 10 to the 10, all the way down to 10 to the 4. We want to know what this time to reduce the number concentration by a factor of 2 is. So let's start by getting an expression for this. In class, for monodisperse coagulation, we had this number concentration over time that looked like this, but we also gave another form for it that looks like this. This is just rearranging that first version. Again, in this case, since we have no information about the size of the particles, we only have number concentrations, then we're just going to have to assume that beta is approximately 1. We have no information from which to calculate it. Then I'm going to multiply through everything by n naught. And if n over n naught is 1/2, then this is the inverse of that. It's 2 minus 1, and that's going to then give us an expression for t sub half. So t sub half equals 1 over the coagulation coefficient times the initial number concentration. So we were given a coagulation coefficient of 3.33 times 10 to the minus 10 cubic centimeters per second. So let's use that first number concentration. If we do that, then we get quite a small time, 0.3 seconds. So in less than a second, that aerosol number concentration has been reduced by a factor of 2. And then just moving down this column, right, to lower number concentrations, if that initial number concentration is lower, right, the time to reduce the number concentration by a factor of 2 will increase, right? There's an inverse proportionality here. And so we expect the times over here to be increasing. And since this is decreasing by factors of 10, then correspondingly the time should be increasing by factors of 10. So for example, if we put 10 to the 9 down here is our initial number concentration, then we would get an aerosol half-life of 3 seconds. So I'll do it like this. I can stay on the camera. 3 seconds. And then 30 seconds, and so on. I guess there's 10 to the 6, which corresponds to 3,000 seconds. All the way down to 10 to the 4th. And by 10 to the 4th, then we get that it takes about 3.5 days for the aerosol concentration to be reduced by a factor of 2, right? So all the way from less than a second at the very highest number concentration to 3.5 days for the lowest number concentration. So this is, again, that idea that the rate at which coagulation proceeds is proportional to the number concentration. Another way of saying that is that the reduction in the aerosol number is proportional to that aerosol number. So the more particles I have, the faster their number is going to be reduced by coagulation.